All right, so here's an interesting, potentially interesting physics problem for you that you may enjoy. So suppose there is a ramp that it came out as a cliff in my drawing, but it has a height h, and on top of the ramp there is a motionless car. Uh, there's a little car here. Alright, so the speed of the car is equal to 0. And then the car rolls down the cliff. Okay, and then there is no energy loss in this descent, and then the car is just rolling on the plane. And the speed of the car with which it's rolling, it's easy to find using conservation of energy. So we need to say that energy before the car rolled and after it rolled down are the same, and before it just had potential energy, so I'll just write it down here, mgh, and after it rolled down the hill, the potential energy is 0 because the height of the car is 0 now. It only has the kinetic energy, so it will be just mv squared divided by 2. And then I can solve this equation for the velocity of the car, cancel mass, and then I find that car's velocity is equal to, at the bottom, is equal to square root of 2gh. Right? So the speed is 2gh. So that wasn't so difficult. But now let me look at this problem from a different perspective. So suppose I'm observing the same phenomenon of car rolling from the cliff with from a moving system of reference. I'll just draw it here. So it's x, y, and z. So the system of reference is moving to the right with exactly the same velocity as the car's velocity at the bottom of the hill. So the speed of system of reference is equal to square root of 2gh. Okay, so the laws of physics are supposed to work in every system of reference. So it doesn't make a difference for me whether I look at from the stationary system of reference with respect to the hill, or whether I just look at the same phenomenon in the moving system of reference with the constant speed of square root of 2gh, right? So let me write down the conservation of energy in this moving system of reference. Now, in the moving system of reference, the velocity of the car before it rolled down is actually directed to the left, so velocity will be equal to minus square root of 2gh, right? And after the car rolled down the hill, because the system of reference is moving with the same speed as the car, the velocity will be 0. So the total energy of the car before it rolled down the hill will contain both potential and kinetic energy components now. The potential energy will be mgh as before, and there will also be a kinetic energy component, mv squared divided by 2, where v is the speed. So both of those numbers are positive because height is positive and v squared is positive. And that should be equal to the total energy of the car after it rolled down the hill, and that is equal to the potential energy. Potential energy is 0 because the height of the car is 0, plus the kinetic energy. But kinetic energy is also 0 because velocity of the car in the moving system of reference is 0. So I have to conclude that the total energy of the car after it rolled down the hill is 0. But before it was something positive. So energy somehow magically disappeared. So I hope you will be able to explain me how and where it disappeared. And please try to be quantitative. I mean, for a full solution of this problem, you have to actually describe where and how much energy went. And I hope you guys enjoyed this program as much as I did. If you want to post your answer, please do so either in the comments of your below the video, or you could also give a video response to this remarkable puzzle of vanishing energy. Good luck, and until next time, bye.